So if a particle is going in a circle, and let us say the object is going this way with some velocity v, its velocity is changing direction. The speed is constant, but the velocity is changing direction. I am only looking at uniform circular motion. We are only looking at uniform circular motion. So that means, what is uniform? The velocity is not uniform, speed is uniform. Angular velocity is uniform. So uniform means omega is constant, speed is constant, velocity is not constant. Velocity is definitely changing. And the velocity vector, which was like this, is now going to become like that. And last time we saw that the acceleration of the particle is going to be like this, and the acceleration is v square by r. If this is radius r, acceleration is v square by r. Okay. We also saw other forms of this. You already know that v is r omega. So if I look at v as basically r omega, I'll get r square omega square by r. So it basically becomes r omega square. But both of these come from the simple idea that A equals v omega. V equals r omega, A equals v omega. That is the symmetry you must think of. Basic idea here is that v changes this r. The reason this r goes around is because of this v. V makes this r turn around at a rate of omega. So v is the reason this r is turning around. But v is also turning around. If this was v, now the new v is like this. So v is also turning around at the same rate. So the rate at which v is turning around is the same as the rate at which r vector is turning around. This radius vector is turning around at the rate of omega. But v vector is also turning around at the rate of omega. You can see that very easily. So for example, if I started with v like this, r was like this, by the time r goes around, v will go around also. So when it comes back, v is going to be like this. So that means v started like this, then became like this. You bring it here, you will see that v also turned around. When v is here, you bring it back to the same place. This v became this v, became this v, became this v, and then back to this. So v is making a full turn. The only difference between v and r is you can see that r is making a nice circular turn. You can't notice v is making a circular turn because v, we are saying, is here, is there, is there. Right? But it is going around. If you bring all the v vectors to one place, so for example, if I had said that the velocity was here like this and the velocity was there like this, you can't see that it's actually making a turn. But if I brought it here and kept it, you can see that it's nicely making a turn. And after some time, the velocity vector here is going to be like this. So what is all that is happening is that the velocity vector is going around and coming back. And how much time does it take to do this? Exactly the time that this particle takes to go around. So the time in which the radius vector makes one full turn is the time in which the velocity vector will make one full turn. So who makes the radius vector turn? Velocity. So how fast is the radius vector turning? Angular rate is omega. V equals r omega. Who is making velocity vector turn? Acceleration. And the acceleration is making it turn at the rate omega. So this is v omega. So actually they are very similar to each other. So this is very useful and important to keep in mind. In fact, this is the proof also. If we understand this a little bit more carefully, this becomes the proof. So A equals v omega. V is r omega. Suppose I substitute r omega, I'll get r omega square. That is that form. Omega is v by r. If I substitute v by r here, I get v square by r. Okay. So whether you know the derivation or not, this is extremely important to keep in mind. Okay. And if this is the velocity, this is the radius vector. Velocity vector is perpendicular to the radius vector. Acceleration vector is perpendicular to the velocity vector. But if I had a line whose perpendicular I take and then again draw a perpendicular, this and this must be parallel. But if I had made a turn this way, they would have been parallel and in the same direction. But I have made a turn this way, so that means they are in the opposite direction. If I brought this arrow here, remember all arrows are at the particle. The most important idea to keep in mind, you can draw whatever arrow you feel like. You say this is the velocity vector, that is the velocity vector, this is the radius vector. Ultimately, whose velocity vector are we talking about? The particle. That means the velocity vector must be at the location of the particle. Whose acceleration vector are we talking about? Particle. The acceleration vector is there like this, but it's not there, it is at the particle. So you bring it back to the particle. If you bring it back to the particle, what is the direction of the acceleration vector? Towards the center. So this vector, when I bring it to this place, this would be the center. So this is acceleration, velocity, radius vector. So the acceleration vector points towards the center. So we call it centripetal acceleration, towards the center acceleration. Is that okay? So this is the centripetal acceleration, which is v into omega or v square by r omega square. So we know this. First point, the acceleration magnitude is a constant. As you are going around, the acceleration magnitude is a constant, just like the speed is a constant. The velocity vector is not constant. Similarly, acceleration vector is not constant. When the velocity is like this, at this location, the acceleration vector is pointing towards the center. It is always pointing towards the center. It is constant in magnitude, but it is not a constant vector. Hope that is clear. Now, if a particle was going around in a circle like this, and you know that this particle has an acceleration in this direction, it can't just have an acceleration. If a particle has to have an acceleration, there must be a force acting on it. There may be not one force, but many forces. So you can then write force is mass into acceleration, but that is not the full statement, right? What is Newton's law? Net force is mass into acceleration. This guy has an acceleration in this direction, which is v square by r. So that means it must have a net force, which is m v square by r. This net force we call centripetal force. It's terrible terminology, FC or centripetal force. Centripetal just simply means that this force is pointing in this direction. It does not mean that the centripetal force is a new kind of force. It's not like there is a new force called centripetal force. It is actually the usual forces like tension force. Like for example, if I took this ball and I swing it around like this, what is making this guy go in a circle is the tension force and gravitational force. Tension, and when it's like this, the tension is this way and the gravitational force is that way. These two forces together is what? Together. Remember that the net force is what we call centripetal force. It's not even a single force. So is there a new force called centripetal force? No. Like MA is not a force. So centripetal force is not a force. This is not being produced because it's going in a circle. It is going in a circle because there is some bunch of forces making it go in a circle. Those forces are either tension force, friction force, some normal force, somebody pulling, right? All of those forces added up together makes it go in a circle. So all those forces together produce this acceleration. So this acceleration is centripetal acceleration. People spend a lot of time and discussing whether centripetal force is a good real force or centrifugal force is a real force. Actually neither. They are both useless terms. Centrifugal force is a pseudo force, does not exist. It's called a false force. It's wrong. False basically means wrong. Sometimes we will make mistakes and use it. Some mistakes are good. But basically it is not a force that we should talk about right now. Centripetal force is also not a kind of force. This is not a special kind of force. There is no force called mv square by r that is produced. There are other forces that somebody else is exerting, which adds up, and we say that the net value of that force must be equal to mass into acceleration. So the centripetal force produces this acceleration. The acceleration doesn't produce a centripetal force. But because the object has an acceleration, we know that the net force must be equal to mv square by r. But that's not over, that's just the starting point. You know the net force must be mv square by r. Then you start searching and asking who is producing this mv square by r. Maybe the rope, maybe rope and gravity, maybe normal force, friction and gravity. In different situations there may be multiple things that together produce the centripetal force. Does that make sense? So there is no such thing as centripetal force that is being produced. So you will never mark the centripetal force as a force on the object. So when an object is going in a circle, you will mark tension force. You might mark that somebody else is pulling in that direction. So let us say there was an F applied by somebody. Or maybe if the object was here, there might be a tension and there might be a gravitational force. This is a different situation, this is a different situation. I'm just putting it in a diagram. Okay? Now, the centripetal force is not here. So you will write this force minus that force is the net force. This net force is what I am going to call centripetal force. It produces a centripetal acceleration. Look at this equation. How does this look like? Net force is mass into acceleration. But because people call this fellow centripetal force, we will use that term. But remember, it is not a special kind of force. All forces are referred to by who produced them, except this useless term. Okay? For example, if you take the force like spring force, who produces spring force? Do you think that this wooden piece is going to produce spring force? So who will produce spring force? Spring. Who will produce friction force? The friction between two surfaces. Who is going to produce tension force? A rope. Right? If you talk about normal force, usually it is produced by the surface. Who is going to produce gravitational force? Some other mass, maybe the earth. So whenever you talk about a force, it is always connected to who produced it. Electric forces, who will produce? Electric charges will produce electric force. Centripetal force, who produces? It looks like, because of this terminology, it feels like centripetal force is produced by centripetal something. But the only other centripetal you know is centripetal acceleration. So our brains immediately start to look at the word and decide centripetal force is produced by centripetal acceleration, and that is absolute nonsense. It is not true. Acceleration does not produce force. Centripetal force is not produced by the acceleration. The centripetal force is produced by tension, mg, and by a whole bunch of other things. It may not even be one force, it may be sum of many forces. And that produces this acceleration. And unfortunately, we are calling the accelerations, we have a name for it, and we are using this to call the force also centripetal force, which creates a lot of confusion in people's minds. I hope that part is clear. So let us just do a few questions.